SwayamPrabha. Digital India. Educated India.
So, once again let us write the potential function and stream function at a point. So, potential function at any point x y, what it will be? It will be convenient to work now in terms of r and theta. So, we will write r theta. The potential function in terms of r theta is how much? Once again uniform stream along x direction. So, the potential function is u infinity x or u infinity r cos theta, okay. And doublet mu by 2 pi mu is the doublet strength mu by 2 pi cos theta by r. If we want to write psi what is the zero streamline? What will be the zero streamline? See, eventually as we should be take note of this point also, that we can add any constant to this phi or psi, does not alter the solution. Okay. Because when we, even if we have a constant here, those are velocity components, they will not have that constant. When you differentiate to find the velocity field, then the velocity field will not have that constant. So, velocity field is still unique, phi might have some additive constant, that is of no importance. Anyway, so with this, what would be the zero streamline? If we take that constant to be 0, what is zero streamline? Theta equal to 0 is of course a zero streamline. Or r square equal to mu by 2 pi u infinity. What is this? R square equal to mu by 2 pi u infinity, that is a circle. So, zero streamline either the x axis itself, the x axis itself is a zero streamline and also a circular. Still let us make it, let us confirm whether this circle can be represented by a solid body. If it is a solid body, then it will satisfy the boundary condition also. If we want to represent this zero streamline or this circle by a solid body, then our boundary condition also must be satisfied. What is the boundary condition? That the flow must be tangential, or the normal component of the flow velocity must be 0. So, let us find the velocity component. What are the velocity component? U r and u theta. Let us say u r and u theta. U r you can find either as a d psi d r, d phi d r, or 1 by r d psi d theta. 1 by r d psi d theta. Either find d phi d r or 1 by r d psi d theta. What is u r? And similarly u theta. So, is the normal component of velocity 0 on that circle? Isn't it? That u r is 0 and u r is eventually the normal velocity. The radial component is normal to a circle. So, the normal component of velocity is 0 when r is this. So, on that circle, particularly that closed circle, the normal component of velocity is 0. So, that it satisfies the boundary condition there, and that circle can be replaced by a solid body, and then the doublet does not exist. That circle is the effect of the doublet, while the actual doublet is not there. As in case of those oval and all, when you replace the oval, that closed curve by a real oval, those point source and point sink, they do not exist, but their effect is there given by the oval. Similarly, once we have this circle, if we have a circle, that gives the effect of the doublet. If we have a circle in the uniform stream, then this circle is the same as the effect of a doublet. So, this is now flow past a infinite circular cylinder. The velocity field on the surface of the cylinder, now we will call it the cylinder. So, the velocity on the surface of the cylinder, the radial component of 0, and u theta is of course now the tangential component. The tangential component is given by this. You can substitute now what is r. How much is u theta? How much is u theta? Plus or minus? Plus or minus? Minus 2 this is, remember, this is only on the surface of the cylinder or circle, not the complete flow field. The complete flow field, of course, now we can write the complete flow field for a circle, the complete flow field for a circular cylinder. What should be phi, and starting from see, we have a cylinder, we do not have any doublet. So, we should not use mu, but what is mu? Mu equal to 2 pi u infinity r square. Instead of the small r, we are now writing that small r is a variable, it is just a coordinate. For the cylinder, the radius is r. So, what will be phi? Again the stagnation point will be at the two tip of the diameter along x axis, at the tips of the diameter along x axis, just like in case of oval. So, that is at theta equal to 0 and theta equal to pi, two stagnation point at theta equal to 0 and theta equal to pi, x equal to plus minus r. Which you have already done on the surface of the cylinder. Let us now find the pressure on the surface of the cylinder. At any point in the flow field, of course, you can find using these u r and u theta, but it is more important to find them on the surface of the body. So, we will find pressure on the surface of the body. Taking one point at infinity or far away, P plus half rho u r square plus u r on the cylinder surface is 0. So, only u theta square. And what is u theta square? 4 u infinity square it is usual to find pressure in terms of pressure coefficient, or rather in aerodynamics when someone says pressure, he actually means pressure coefficient. So, if you are sometime asked to find pressure, you can leave it at pressure coefficient only, or rather try to find the pressure coefficient, not the absolute pressure. So, the pressure coefficient, as you know, we defined as C p is P minus P infinity by half rho u infinity square. So, what this will be? Hmm? 1 minus 4 sin square theta. So, it is obvious that at the stagnation point pressure coefficient is 1, because at stagnation point P minus P infinity is half rho infinity square. At stagnation point, since the velocity is 0, so P minus P infinity equal to P. So, at stagnation point the pressure coefficient is 1, which you can see from here also, at theta equal to 0 and theta equal to pi, C p is 1. Okay. The C p becomes minus 3, C p become minus 3 at theta equal to pi by 2, and again also at 3 pi by 2. So, on the y axis diameter at the two tips pressure is C p is minus 3, and negative C p means that okay, there is a suction, the pressure there is less than the pressure that is undisturbed, less than P infinity. This C p negative does not mean an absolute negative pressure, because that is not possible. Absolute negative pressure is not possible, but this is with respect to that undisturbed or reference pressure. So, pressure has decreased there, meaning that flow there is accelerating and there is a suction, but this is same at theta equal to pi by 2 as well as 3 pi by 2. Similarly, if you take all the corresponding points or the geometrically similar point, you will see that pressure will also be similar, velocity will also be similar, meaning we will expect a 0 force on it. However, we can, since we now have a very simple expression for our pressure coefficient or pressure, we can completely calculate the forces. What will be the lift force? Once again remember, lift force is the force component which is normal to the direction of undisturbed flow or normal to the direction of the free stream. So, in this case the free stream is along x, so its normal is y. So, y component itself is the lift force, but please remember the y component or what we call the vertical component is not necessarily the lift force. The lift is normal to the free stream direction, normal to the free stream direction, which happens to be in a real aircraft the direction of the flight. Okay. So, the lift force is with respect to an aircraft is normal to the flight velocity, and here we will call it normal to the free stream. Sometime it may coincide with your y axis, sometime may not. So, what will be the lift force? The pressure acts always normally, it is the normal component of pressure force, but normal to the body is not normal to the flow. Pressure always is normal to the body, and normal to the body means along r. So, what will be the y component? Y component of the force? Yeah, the result will be 0, but at this stage I am not asking that final result. We want a general expression which you can use for other cases or it will not be 0. Yes. Sorry. this is the direction of the pressure. So, what will be the lift force? Consider a small length r d theta, okay, and consider a unit width, because this is infinite body. So, we cannot find it completely, we have to consider only for unit width. So, if we consider a unit width, that is length along y direction, sorry, the z direction, then area of that strip is r d theta into 1. So, pressure into that area, that will give the force, and then yes, a component of it, that is the total force, no, a component of it, sin theta. However, there will be a negative. Yes. That P minus P infinity can be written as half rho infinity square C p. Then half rho infinity square can be taken out, okay. Now, this C p you can integrate and see that it is 0. Okay, integration is from 0 to 2 pi. Okay. Similarly, the drag force is all the same, only the cos theta component. So, here also again a situation where the flow is perfectly symmetric, flow has perfect symmetry both with respect to top and bottom as well as front and rear. And not only that, since circle or cylinder has such a symmetry that even if your flow direction changes, the body is still symmetric. there are certain cases where if your flow direction changes, then the symmetry may be lost. So, in that, consider the case of the Rankine oval. In that case, if the flow was in x direction only, it was symmetric, but if the flow direction made some angle with respect to the x axis, then it is no longer symmetric. But for a circle, if your flow direction changes and makes certain angle with respect to this, the diameter that you are considering earlier, but then it becomes symmetric with respect to another diameter, and again with respect to that diameter the body is symmetric. So, whatever the flow direction you make, it remains symmetric. And this flow about a circular cylinder will neither give lift or drag in any situation. For an incompressible in VCT rotational flow. However, as you know that this is not of course a real solution. It always gives drag, it always gives drag, you can never make it 0 drag. Lift, okay, there are many situations where it does not produce lift, but drag is always there. However, we do not get it. So, first thing, if we, what we need to get some force, that if we can make the flow asymmetric, if we can make the flow asymmetric, and see this simple way to make this flow asymmetric will be if we put a point vortex also or an infinite line vortex at the center or at the origin where the doublet is, then you see how the asymmetry will be made. A point doublet produces a circular streamline. Now, you see that with respect to that doublet, or if you think about say as a top and bottom of the doublet, you see the flow direction is indifferent, flow is in different direction. A circular flow, on the top it is along this direction, on the bottom it is along this direction. So, it will increase the speed on the upper half, decrease the speed on the bottom half, and an asymmetry will be created, particularly top bottom asymmetry, and we can get a lift force. However, before we try doing that, let us look to this uniform stream and doublet, but in a 3D case, where we have considered here a 2D point doublet, which is an infinite line doublet. Instead of an infinite line doublet, if we consider a truly point doublet, then we can guess that okay, our body will now be sphere. Instead of an infinite cylinder, we will have a sphere. Let us check that. So, then we will come back to this again. Then what will be the potential function? The potential function in the r theta plane. In the r theta plane, once again it is u infinity r cos theta plus, what is the potential for a point doublet? Potential for a point doublet. Mu by 4 pi r square cos theta. Mu by 4 pi r square cos theta, and the velocity components u r d phi dr or 2, it should be 2. What will be u theta? So, here also see that the radial component of the velocity will be 0 for r cube equal to 2 pi mu by 2 pi u infinity. The radial component of velocity is 0 for for theta equal to 0 as well as for that. So, we get here again Once again, what will be the velocity on the surface of the sphere? Minus. So, you see that the tangential velocities are less than what they were for the cylinder magnitude wise. It was 2 u infinity sin theta, now it has become 3 by 2 u infinity sin theta. That means, in case of a sphere, the flow acceleration is less. The maximum is again at theta equal to pi by 2, which will be minus 3 by 2 u infinity. In case of a cylinder, it was 2 u infinity. So, at theta equal to pi, the flow velocity was 0 and it increases to 2 u infinity in case of cylinder, while it increases up to 3 by 2 or 1.5 u infinity in case of a sphere. So, flow has accelerated less, and that will be reflected of course in pressure also. If we look for the pressure coefficient, what it will be? Once again we can write that P infinity plus half rho U infinity square equal to P plus half rho or instead of 1 minus 4 sin square theta, we have 1 minus 9 by 4 sin square theta. Less suction than what it had in case of a cylinder, smaller pressure difference. This eventually a general result, that whatever velocity increase or pressure difference is created in 2 dimensional flow, in 3 dimensional flow it is much less. the pressure difference that is created in 3 dimensional flow is less than what it happens in 2 dimensional flow. That means, in 3 dimension the flow is much relieved than in 2 dimension, and this is eventually known as a 3 dimensional relieving effect. The flow is not that stressed as in case of 2 dimension, it is much more relieved, much more relaxed. Why does it happen? Because in 3 dimension the flow has one additional direction to adjust itself, while it is not there in 2 dimension. In 3 dimension the flow has one more dimension or one more direction in which it can adjust itself. In 2 dimension it does not have that liberty, it cannot adjust in the third direction, because in third direction it is infinite. So, it cannot change anything, but in 3 dimension it can change in the third direction also, and consequently it is much more relaxed or relieved. So, it is a general result, not restricted to only inviscid, incompressible, irrotational or ideal flow, it is true for all flows. However, the magnitude of relaxation or magnitude the relieving effect, that might change a little bit, but the relieving effect is always present even in real viscous flows, rotational flows or even in compressible flows. In all cases this relieving effect is present. The amount of relief may not be same, is or rather not same, it is different, but the relieving effect is always present. So, as far as that qualitative result is concerned, that when we go to 3 dimension the flow is relieved, then in 2 dimension that general result is valid under all circumstances. Now, let us come back to that cylinder once again. As we said that we will now place a point vortex or an infinite line vortex at the location of the doublet itself. That is, doublet and vortex are at the same location. So, uniform flow, of course, in the x direction, let us take at the time being, plus infinite line vortex, plus infinite line doublet and we will consider a counterclockwise doublet, that is minus gamma. We will consider a counterclockwise vortex. So, the strength is minus gamma. Okay, as before, this uniform flow plus infinite line doublet, we will create that flow about a circular cylinder, and if the doublet strength is mu or if the cylinder radius is r, then the doublet strength should be 2 pi r square, 2 pi u infinity r square. that part remain valid, because this is just a superposition. The whatever we have found earlier, that remains. It is not that this is going to change everything. These are just linear superposition. So, whatever we had with uniform flow plus infinite line doublet, that remains as it is. That uniform flow plus infinite line doublet gives flow past a circular cylinder, and the radius of the circular cylinder is related to the doublet strength. That part still remains, that is not changed. In addition to that, we now have an infinite line vortex. So, the potential function, as before, we can write phi say r theta is what? Uniform flow plus infinite line doublet, how much was that? U infinity cos theta r plus r square by r, or u infinity r plus r square by r cos theta. This is uniform flow plus infinite line doublet, where that representing a cylinder of radius r. Now, we have a counterclockwise vortex. So, what will be the potential for that counterclockwise vortex? Potential for a vortex. Potential for a vortex or stream function for a this we did earlier, stream function for an infinite line vortex. Stream function is gamma by 2 pi r, and vortex potential function is gamma by 2 pi theta, or gamma is the strength. Okay, we have taken a counterclockwise, so it is minus gamma by 2 pi theta. Similarly, psi we can write u infinity what are the velocity components? See, a point doublet, it gives only tangential velocity, it gives circular streamline. Just a point vortex alone gives only circular streamline and only velocity, tangential component of velocity. So, the radial velocity component remain unchanged, whatever it was. And obviously, it remains that at r equal to r, this is 0. That means, it still remains flow about a circular cylinder of same radius. That addition of point vortex at the center does not change it, it still remains flow about a circular cylinder with of radius r. However, that tangential velocity component changes. What will be the tangential velocity component? What will be the tangential velocity component? This part remains minus u infinity 1 plus r square by r square sin theta sorry, this is so, since the tangential velocity component changes, so on the surface of the cylinder, which we are more interested, you see now the stagnation points are no longer at theta equal to 0 and theta equal to pi. The stagnation points are no longer at theta equal to 0 and theta equal to pi. And for this counterclockwise, clockwise, sorry, I by mistake I have written clockwise, it should have been clockwise vortex. Okay, please make that correction. By mistake I wrote that we are adding a counterclockwise vortex, it should have been clockwise vortex we are adding. We will later on see why we are adding clockwise vortex. As far as the mathematics is concerned, if we add a counterclockwise vortex also, nothing will change, only that sign will be plus, other than that nothing will be changing, but why we are using clockwise, that we will see later on. The first thing you can see here that the stagnation points are changed, they are no longer at theta equal to 0 and theta equal to pi. And for clockwise vortex or clockwise circulation, we will see that these stagnation point are coming below the axis, coming to the bottom up, and the location is of course dependent on this value of gamma. At different value of gamma, the stagnation point will be located at different position. And not only that, it may so happen that the stagnation point will no longer be on the surface of the cylinder. Anyway, we will continue that in the next class.